Okay, we're back to hopefully finish up the notes on simple harmonic motion, and we're going to do that by talking about pendulums. So I'm going to draw the picture for the pendulum first, and then I'll explain what this small angles only text means. So a pendulum is a very simple, it's a very simple setup. In its most simple form, what it consists of is a string and then a mass attached to the end of it, and the mass is called a bob. So here's our pendulum. We're going to say that it has an anchor point right here. We're going to say that the pendulum has been brought back to this point right here, which we're going to label A. And then if we release the pendulum, it will swing down to points B, C, D, and E. And then it would swing back. We are again going to assume that there is no damping going on, so that ET is equal to ET. And like we did last time with the springs, we are going to discuss the sizes, the magnitudes, the directions of the different variables that we can measure here. We're going to be measuring 7 of them here. There's no springs here, so there's no elastic potential energy, but as you can see, we don't have motion in just one direction now. We kind of have motion in 2 directions. So we're going to analyze the X and Y positions. We're going to be analyzing the velocity. We're going to be analyzing the acceleration, the kinetic energy, the gravitational potential energy, and the net force on the object. And we're going to start off at A. So at A, as far as the X position goes, this is pretty much as far to the left as it goes. And actually, so when we get to C, we'll talk about this again. But we're going to set our 0 coordinate right here in the middle at this equilibrium spot. If we were just let the pendulum hang straight down, this is where it would hang. This is the equilibrium for the pendulum. Okay. Matter of fact, I'll label that EQ for equilibrium for C. Okay. And again, we're transitioning between all of these states. Alright, so if this is the equilibrium spot, then A is as far to the left as it goes. So I'm going to say that the X position is at its negative maximum here. As far as the Y position goes, this is at its maximum at A as well, because that is the highest that it ever gets. If we're calling C position 0 for the Y direction, then A is as high as it gets, so we'll just call that a maximum. Since A is the release point, it's obviously not moving yet, so the velocity is 0, and therefore we know the kinetic energy is also 0. Since we know that the Y position is at a max and the gravitational potential energy is dependent on the Y position, the height of the bob, we know that since the Y position is at a max, the gravitational potential energy is also at a max. And that just leaves the force and acceleration to talk about. Just like with springs, where the more displaced the object was, the greater the force. In other words, the restoring force in that case was the spring force. In this case, the greater displacement leads to a bigger restoring force on the bob. But it's not, and that comes from gravity, but it's not the full component of gravity. We know that gravity points straight down. For our case, the restoring force for the pendulum is not exactly, it's not the full force of gravity, because some of the force of gravity does not point in the direction that the bob is about to accelerate in. Instead, it's the component of gravity that points perpendicular to the string, in other words, in the direction that the bob is about to start moving in. So if you think about gravity as being pointed down this way, the component that we're looking at is this component of gravity right here. That's the restoring force. And if you visualize this, as the pendulum bob moves farther down towards equilibrium, the component that is in the direction of the acceleration is going to, the component of the force that's in the direction of the velocity decreases. Okay? Here we have velocity, let's see, we have gravity still pointing straight down, but the component that is in this direction, perpendicular to the length of the string, is smaller. When we get to C, gravity points straight down, there is no component that is in the direction of the velocity. It's perpendicular to it. So you can see that that component of the force of gravity decreases as the object moves from A down to C. It would then increase and point in the opposite direction as the object moves from C up to E. So that is where our restoring force in this case comes from. It comes from the component of gravity, of the force of gravity, the interaction between the bob and the earth, that is perpendicular to the tension, to the length of the string, or in other words, in the same direction, parallel to the velocity at that point, because that's the force that causes it to speed up and slow down. Up here, where we have the biggest component of the force of gravity in the direction of the acceleration, that means that we have the biggest net force in the direction of the object's motion that we're going to have. So the net force is at a positive maximum. That means the acceleration is at a positive maximum. Okay? And we can look at demonstrations in class and see and work that out a little bit more. But that's a little bit of a confusing concept. But the acceleration, the tangential, we would call it the tangential acceleration, which is the acceleration that speeds up and slows down the pendulum, is at a maximum here because the net force in that direction is at a maximum. As we move along to B, B is at an intermediate position. So what I'm going to do with B is I'm going to talk about these quantities in terms of the relationships to A and C. So actually maybe I'll do C first when we're all the way down at equilibrium. So let's do X, Y, V, A, K, UG, and F. All right. We already said that equilibrium is going to be the our coordinate, our origin for our coordinate system. It's just usually easier that way. So we're going to say that X is 0 and Y is 0. The gravitational potential energy, because Y is 0, must be 0. And that means, since all the energy is conserved, and initially we had all gravitational potential energy and we had no kinetic energy, that means that the kinetic energy must be at a maximum here, which in turn means that the velocity must be at a maximum here. Okay? Doesn't matter whether it's positive or negative for the velocity, because it could be either way, depends on which way the object is moving. As far as the net force on the object, and here we're talking about the net force in the direction of its motion. The net force here would be tension pointing straight up, gravity pointing straight down. There is no force to the left or right in the direction of its motion. So the net force in that case is actually 0. There is a centripetal force, remember that just means net force towards the center of the circle, pointing up, but that's not causing any speeding up or slowing down. We're kind of looking at something a little bit different here. So it's not that the net force, maybe I'll make a note of this. Tangent, oh, can't write it there. Tangent to motion. That's what we're really looking at here. Because we're talking about this restoring force in terms of making it something speed up or slow down. The centripetal force is important for making the object change direction, but that's not really what we're talking about here. We're talking about the force that's making this object speed up or slow down. Since the net force in the tangential net force is 0, that means the acceleration of the object in its the tangential acceleration of this object is 0. Okay, let's actually go and talk about B now, because B is kind of an intermediate position. We know that, well, actually, here, let me write these down first. X, Y, V, A, K, U, G, F. So we know that A is where X is at its most negative and X is 0 at C. So that means that this X for position B must be kind of somewhere in between them. So we could say that X here is just greater than what it was at A. Likewise, for the Y position, we know that it started off at a maximum at A and it goes down to 0 at C, so we can say that this is less than A. Since the object is speeding up while it's at B, we know that the speed is greater than it was at A. Or you could also say less than it is at C. Matter of fact, yeah, that's what I'm going to go with. You could say greater than A. I'm going to say it's less than it is at C, because we know at C it's a maximum. They're equivalent statements. Let's see here. The acceleration, we know it's less than it was at A, because it started off at a maximum, goes down to 0. The kinetic energy follows the velocity, so that should be less than c, or greater than a, however you want to call it. Gravitational potential energy follows the height, or the y-coordinate, so that's also less than a. And the force, the restoring force that causes the oscillation, that causes the speeding up and slowing down, that makes this, if you were to graph the position, it would make a sine graph. That force, the force tangent to the object's motion, is less than it was at A. The restoring force is decreasing because the object is not as far displaced at B as it was at A. Okay? So we see that a lot of things are either decreasing or increasing as we go from A to B towards C. I can do the same thing with D and E. I'm going to start with E again, and then we'll go back to D, excuse me. X, Y, V, A, K, U, G, F, X, Y, V, A, K, U, G, F. All right. So as far as E goes, this is kind of the mirror image of A, right? The only real difference is that the X position is now at its positive maxima as opposed to its negative one. The Y position is as high as it goes, so that's also at a maximum. This is the turning point, doesn't go any higher. So at this point, it's kind of stopped momentarily and it's about to start going back down, but right now it hasn't started yet, so that means that the speed is 0, the velocity is 0. The acceleration now points back this way. There is a tangential acceleration in this direction caused by the gravitational force at this, with a component of the gravitational force at this point, points back towards equilibrium, so that's a negative maximum acceleration. Kinetic energy follows the gravitational potential energy, so that's 0. Kinetic energy follows the velocity, so that's 0. The gravitational potential energy follows the y-coordinate, so that's at a maximum. And the force follows the acceleration, so that's at a negative maximum. And as far as D goes, now I'm going to make references to either C or E. The Y position, you could say it's greater than C or it's less than E. Or, excuse me, the X position. The Y position, same way, greater than C or less than E, however you want to reference it. The velocity, you could say that it is less than C or greater than E, because E is 0. So I'm going to say greater than, or I'm going to say, yeah, less than C. The acceleration is either greater than C or less than E. The kinetic energy, again, is either less than C or greater than E. If I'm saying these backwards, I apologize. I might have slipped in there. Gravitational potential energy follows the height, so that's less than E. And the force follows the acceleration, so that's also less than E. Okay? So we see how a pendulum works, how these quantities change as you go from one position to the next. The acceleration increases as you go out with farther displacement, and the kinetic energy increases as you go toward the middle. Gravitational potential energy increases as you go up. The velocity, increases as you go toward the middle. The restoring force increases as you become more displaced, and so on and so forth. Again, the questions on this topic won't be straightforward, won't be like make a table like this. They will be something about testing about different parts of this table. Okay, so you should be able to fill out this table on your own and justify why your selections are the way that they are. Again, we're going to do this later in class, but we might want to think about what sort of factors affect the period of a pendulum. Some common ones that might be examined. You might want maybe the length of the pendulum. You've all seen a grandfather clock with the big with the big pendulum, and that's how it keeps time. Does changing the length of that pendulum increase or decrease the period? How much time it takes to go from A all the way to E and back? Remember, it has to go back to its initial spot. So one period would be from A all the way to E and then all the way back to A. Okay, not just from A to E. That's half a period. So does the length affect the amount of time that takes to happen? Does the mass of the pendulum bob affect that? because if the mass of the pendulum bob, well, that's going to increase the component of the force of gravity. That seems like it could have an effect. Seems like the length could have an effect. Does the angle matter? I'm going to answer this one for you right now, actually. Okay, we're not going to talk about the actual equation yet. We're going to do that in class. But this part that says small angles only, and I know my picture is going to be a little misleading when it comes to this. Small angles only means that all of this analysis and this idea of simple harmonic motion, well, I guess the variables are fine for what we just did. But as far as the period of a pendulum goes, you can only use the equation that we're going to come up with and call the motion of a pendulum simple harmonic motion for small angles. That means angles under about 30 degrees. 30 degrees is the limit. Okay? For larger angles, the pendulum still oscillates back and forth. I'm not saying that these things aren't true for those larger angles, but we can't call it simple harmonic motion anymore. Not an example of simple harmonic motion. By the way, this idea that you have to use angles under 30 degrees is called the small angle approximation. Okay? Oh, I just realized you guys can't really see that. So that's called the small angle approximation. And this really only has to do with the period equation that we're eventually going to derive. You can only use that equation to calculate the period for pendulum motion that is where the maximum displacement is less than 30 degrees. And the reason for that is that the actual motion of a pendulum is proportional not to the angle of the displacement, but actually to the sine of that angle. But if you use small enough angles, and you can try this on a calculator, if you use small enough angles, then the, what is it? It's, I always have trouble stating it. Then it doesn't really matter what, the answers are close enough so that it works. In other words, if you take the sine of an angle, if you take the sine of an angle and then you compare that to just the value of the angle in radians, as long as the angles are under about 30 degrees, it's